Hi, and welcome to video 5.2, a video in which we're going to write the code to solve the generalized eigenvalue problem that corresponds to solving the Hartree Fock equations in a finite basis set. Okay, so in general, the equation that we're going to be looking to solve is the Fock operator, which will include the single electron Hamiltonian and our approximation to the electron-electron interactions through the Coulomb and exchange operators. Will make up the F matrix. We're going to be searching for the eigenvectors of that, so that when we have so that we get an eigenvalue out times the overlap matrix times our eigenvectors again. So this is a little bit different than the reason why it's a generalized eigenvalue problem is because of this S matrix that we have the overlap here. Okay, and so as we said last time, our strategy is we're going to start by finding the eigenvectors and eigenvalues of our overlap matrix S. We're going to use those to create a new matrix X out of the eigenvalues and eigenvectors, and this will transform our Fock operator. We're going to transform it from F to F prime. Then we'll find the eigenvectors and eigenvalues of F prime, and then we'll convert those back to our atomic orbital basis set by applying this transformation again. Once we have the eigenvalues and their associated eigenvectors, we're going to build a density matrix using the n over 2 lowest states. So we're going to be putting 2 electrons into each level. And then this comes with a little bit of a small little widget. When MATLAB returns the eigenvalues and eigenvectors of a state or of a matrix, it doesn't do any sorting. If you're doing this in Fortran or C and you were using, say, the LAPACK routines, it would come out sorted. MATLAB doesn't sort them, so we need to do that ourselves. And we want to take the n over 2 lowest eigenvalues and associated vectors. Once we have a density matrix, then we're going to build our Coulomb and exchange operators using this new density matrix. Once we have our new Coulomb and exchange operators, we can have a new Fock operator. We'll evaluate the energy, and then we'll do this whole process over again. And we're going to keep iterating over these steps until our delta E is below some threshold value. And we're going to say 10 to the minus 6 Hartrees. Okay, and that's going to be our plan of attack. So let's hop over into MATLAB and go ahead and get started. I'm going to start by writing the SCF routine first, and then we're going to go back and fill in a couple of different routines that we're going to need to add in afterwards. So let's start by doing the following. Edit SCF. This is going to be a function, min E equals SCF. We need our original input, our single electron Hamiltonian, our 4-dimensional matrix of electron-electron repulsion integrals, our overlap matrix, and the total number of electrons that we have in our system. Once we do that, we have a couple of little housekeeping details. We need to know how many cycles we're willing to let it go. So let's say max cycles equal 30. We need a Boolean value to say if we've converged or not. We're going to use that to exit a while loop. So let's just call that converged. And I would add a question mark there if I could. Equal 1. And then we need to label the current cycle, and we're starting at cycle number 0. Okay, so our first step we said was we needed the eigenvalues and eigenvectors of the overlap matrix. And so the way that we're going to do that is to use the built-in MATLAB function eig. Okay. And so this is going to return two things: a vector V, a matrix V where each column will be an eigenvector of S, and D will be a diagonal matrix where each element along the diagonal will be an eigenvalue, and the nth diagonal element will be the eigenvalue for the nth column vector of V. So just a little bit of notational bookkeeping there, nothing too urgent. And then we're going to create our new matrix S, which is going to be equal to, let's see here, V times D minus point. So 1 over the square root of the eigenvalues times V transpose. And so the little apostrophe there in MATLAB takes a transpose of the matrix, or the Hermitian conjugate. Okay, So now we have our new matrix X that we're going to use to transforming from one space to another. And now we just need to get started. And so as a first guess, we're going to solve the one electron Hamiltonian and use its eigenvalues and eigenvectors as our starting point to build the electron-electron repulsion, the Coulomb and exchange operators, and then to start in our actual Hartree Fock routine. But we need that initial guess, and so we're going to start by just saying F equals H naught. So just our single electron Hamiltonian. F prime equals X transpose times F times X. Okay, and now we need to solve for the eigenvalues of this matrix. We're going to call them C prime epsilon equal eig F prime. And so again, C prime will be the matrix of column vectors, which are eigenvectors of F prime. Epsilon will be the diagonal matrix of eigenvalues. We now need to transform this back into the atomic orbital basis set. So C is equal to, let's see here, make sure I get this right. C is equal to X times C prime. All right, so now we have our eigenvectors in terms of coefficients of our atomic orbital basis sets. Okay, so now that we have that, we need to sort that to pick out the lowest, the eigenvectors associated with the lowest energy eigenvalues. And so we're going to write C epsilon equals sort eigs C epsilon. So we're just going to sort them. We'll have to write a routine to do that. We'll then next make a density matrix, D equal build density C, and then we need to give it the number of electrons. Okay, we'll need to write that one as well. And now that we have a new starting density based on the eigenvectors of our one electron Hamiltonian, we're ready to start building the Fock operator and building the exchange and correlation operators as well. So while in cycle less than max cycle and converged not equal to 0. So we're going to change that to equal if we think we're converged. We're going to do the following loop. In cycle equal in cycle plus 1. We're going to build our Coulomb and exchange integrals. Build Coulomb exchange. All right, and we need to give that our density matrix and our four center integrals. F Fock operator H naught plus G. Okay. Now we're going to transform that again. F prime equal X transpose times F times X. We're going to solve for those eigenvalues. C prime epsilon equal eig F prime. Let's transform that back. So C equals X times C prime. Let's sort them again. C epsilon equals sort eigs C epsilon. Okay. Now we need to build a new density matrix. D equal build density C and N. We have our new density matrix. We can now evaluate the energy. So the energy we're going to of this cycle equals, let's write a program called Fock energy, and then the only thing we need to give that is D, H naught, and F. And so we need our density to calculate the energy. Now we're going to see if that is lower than the previous cycle. So if in cycle greater than 1 and the absolute value of E in cycle minus E in cycle minus 1 is less than 10 to the minus 6 Hartrees. Sure, good. Yep. Then, oh, we don't need then. Converge equals 0. And so, and F, right? And so we get through this. If our energy hasn't changed from the last one, we're going to say that we're converged, and we'll exit this while loop. Another end loop on the while loop, and then we can say min E equals E in cycle. And that will be our minimum electronic energy. And then the only thing left that we'll need to add to that is our nuclear repulsion, which we still haven't counted for yet. Let's save this. Okay. And now we have to go back and write some of those helper functions. So let's go through here and make sure we get them all. The first one that we wrote was sort eigs. Okay. So we want to get the in lowest eigenvalues and eigenvectors. All right, so let's edit sort eigs. That's function C. Let's call this eigenvex eigenvals equal sort eigs C epsilon. Okay. We're going to, as in almost all of our functions, we're going to just get the set dimensions of the array, size, C. Okay. All right, and now we need to use the sort command for MATLAB. And we're going to have it return the sorted vector, sorted eigvals, and an index to let us know what their order is, equals sort diag epsilon. And now in B, sorted eigvex, comma, we're going to make column vector equal C index of n in that whole column. C index, sorry, all rows index. And there we go, that looks better. And then we get eigenvals equal sorted eigvals, eigenvex equal sorted eigvex. Okay, and so that will sort all of our eigenvalues and eigenvectors. Okay, let's save that and go back over to SCF. We did, the next one that we need is the build Coulomb exchange. So, edit, build Coulomb exchange. Yes. Function. And that's going to put out an operator, a matrix G, build Coulomb exchange. We need a density matrix and our force center integrals. Make sure that we just put that in the right order. Yep. Okay, great. Okay. All right. Again, we need to get the size. NB equals size D1. G equals zeros, NB, NB. Okay. So now we're going to loop over our four-dimensional matrix GABCD. So for A equal 1, 2, and B, for B equal 1, 2, and B, for C equal 1, 2, and B, and for D equal 1, 2, and B. GAB is equal to GAB plus density of CD times 2 times GABCD ABCD. So this will be the Coulomb integral minus GABCD of ACBD. So we're swapping basis set 2 and 3 to get the exchange integral. All right. And that should be it. And there we go. Well, let's actually just change this to make sure there's no confusing here. Out G. Okay. So now we've built our Coulomb exchange operator. All right. I believe the next one is going to be to build density. Yep. Okay. Edit. Build density. Here we go. Apparently I'd already written this one. So this is out equals build density. We take our eigenvectors and the number of electrons in. We get the size. We start it equal to 0. And then we loop over all of the elements for n equals 1 to nb, for m equals 1 to mb, and then for I equals 1 to n over 2. So we're going to take the n over 2 number of eigenvectors, and d sub nm equals d sub nm plus eigenvex n, comma I times eigenvex m, comma I. So this is getting your density matrix elements. Loop over all of that, and then output the density. I just want to make sure we have eigenvex n, and we wrote this as eigenvex n. Okay, great. So build density looks good. And then finally we have the Fock energy. Edit Fock energy. Right? And that's going to take, please do, function Fock. Oh. Out equal Fock energy. D, our density matrix, our 1 electron Hamiltonian, and our Fock operator. Size D. Great. We're going to start our energy equal to 0. For n equal 1 to nb, for m equal 1 to nb, E equal to E plus D and m times h naught n comma m plus f n comma m. In and then out equal E. Okay, so that will give us the Fock energy. And so let's go ahead and take a look back at our SCF routine. That should be all of the things that we need to do. So let's try at this point. If we go back to our HF driver, we've now written everything except the nuclear repulsion. So if I comment out this line, this should be a program that actually runs. So let's try HF driver ZAL. We have a little bit of a problem in here. Build density apparently does not exist. Line 18. Edit build density. Aha, I see. Okay, so that was a mistake on my part, so let's just make sure we build this correctly real quick. Function out equal build density eigenvex n. NB equal size eigenvex. 1 D equals 0 NB and B. For n equals 1 to NB, for M equal 1 to NB, for I equal 1 to N divided by 2, D of NM equal D NM plus eigenvex N comma I times eigenvex M comma I. Okay, N out equal B. Okay, so it should not quite max cycle. And I thought that was the first max cycle. Oh, silly us, max cycle. Okay, and so that looks like the right number. The last thing that we need to do then is go back to our HF driver and build one last function, which is the nuclear repulsion. Okay, so the last thing we need to do is write our nuclear repulsion, which we just didn't get around to writing. So let's go ahead and do that now. We're going to write edit nuclear repulsion. And this is going to be a function that returns the nuclear repulsion energy out nuclear repulsion. So all we need are the list of atomic nuclei and their atomic locations. Okay. In atom equals size Al, 1. Okay. So we can get the number of atoms, 0. All right, and so if an atom equal 1, then the energy equals 0. This allows us to do single atom calculations. Else, for I equal 1 to n atom, for m equal 1 to n atom, distance equals square root the sum Al I comma that minus Al m comma colon dot char 2. Right, so we're just going to get the distance between each of them, and then energy equal energy plus z sub I times z sub m divided by distance. And n. And we're missing one thing. This is not quite right. I plus 1. Okay, there we go. So now we're going to loop over, we're not going to double count atoms basically. So we're going to loop over all of the nuclei, and that should be good. Okay, so now let's do that little trick again. HF driver, Z and Al, this is 2 hydrogen nuclei. And out. Let's go take a look at that. Out equal energy. Okay, and there we have it. That is the total electronic energy within the Hartree Fock approximation of 2 hydrogen atoms located 2 Bohr apart from each other. So all in all, this is actually not that much code, and it didn't take that long to write. Let's try something else. Let's go Z equal 1, 1, and Al equal 0, 0, minus 2, 0, 0, 0, 0, 0, 2, 0, 0, 4. All right, now let's try this. HF driver Z. Do 4 atoms. All right, notice how it is taking significantly longer to go through 4 atoms. That's to be expected. So this should scale like the number of basis functions to the 4th power the way we wrote it, and we get out what is probably a pretty reasonable energy. We can actually take this, we can do, let's say, we can write a separate little script, right? And we could say for D, let's go D equal 1.0.1 to 3. Size of D. Okay. For I equal 1 to 21. 21. AL, let's see here. Let's try this a better way. AL equal 0, 0, 0, 0, 0, D1. Okay. Z equal 1, 1. Okay. Now let's write a for loop for I equal 1 to 21. E sub I. Sorry. AL 2, 3 equal D sub I. E sub I equal HF driver Z AL 10. So what we're doing is we're changing the bond length in short little intervals between 1 to 3 Bohr and getting out a different energy for each one. This is much slower than using a commercial program for a variety of reasons, but let's see what this looks like. Figure 1 plot D, E. And we get something that looks like a reasonable potential energy surface. Notice how we have a minimum down here, and this is going up. Restricted Hartree Fock is not the way to look at bond making and bond breaking, but at least gives us an idea of where numbers come from when you use them in a commercial program. Okay, so this is how one can get some information out using computational chemistry. Obviously, the next steps here would be to add in angular momentum. I will add several videos showing how to add angular momentum so that we can look at atoms that are heavier than just hydrogen. What that does is it changes the way that we calculate the individual matrix elements, and it makes them harder to calculate, or at least take longer. But the SCF routine doesn't change. Everything that we've learned about the SCF routine stays the same. It doesn't change. It doesn't change based on how many atoms there are. It doesn't change based on how many basis functions. Things just get bigger. But all of the physics and all of the chemistry is contained in the SCF routine. As we've written, adding additional atoms and orbitals and angular momentum just make calculating those matrix elements a bit more tedious, which is why we did it for just 1s orbitals to start with, or s-type orbitals to start with. All right, I will add those to the code and make a separate video on that, and then I will also show you the same program ported over to Fortran. So if you've never seen Fortran programming before, most scientific programming is written in either Fortran or C because it's just faster. MATLAB, for example, is pretty slow when it comes to doing for loops. It's very fast with vectorized math and solving eigenvalue equations, but very, very slow with for loops. And so just writing the same program in Fortran speeds it up by about a factor of 100 to 150. And I'll post that on our website as well. I hope you've enjoyed this. I hope it helps take some of the mystery out of what computational chemistry is and how it actually functions underneath the hood. And I'm happy to answer any questions you might have. Cheers.